Okay, so recording should be on. And I guess we can get started.
Okay, perfect. So hi, I'm Wiktoria. I'm from Poland, as Lucas said, and I wanted to show you two things: strongly connected components and then the segment trees. And we'll do a few tasks from the Polish Olympiad in informatics. If you want to try more tasks of the Polish Olympiad in informatics, I will also send you the link. Unfortunately, a lot of the tasks are only in Polish, but what I discovered today is that some of them are translated to English. So you can just, I don't know, search, see which one are translated. If not, I don't know, you can write to me or ask ChatGPT. That's also a valid option. Okay, so I can either share the screen, but I'd rather just send you the link to some iDrew board. I don't know if you've ever used the iDrew board, but it's really nice because we can all collaborate it there. So please let me know if anybody have any problems with connecting to the board. If so, I will share the screen. But
so to me, it's saying we could not find the board you're looking for if I open the link.
Okay.
Which just sounds pretty promising.
Okay. I'll try maybe to copy the link again.
Yeah, oh, yeah. You missed the letter apparently.
Yeah, I missed the C. I don't know why.
And now it says access is restricted.
Access is restricted. Well, I mean, everybody can write. I think people are already writing something. So it should be fine, I guess.
Doesn't work for me.
Only for you. That's okay though.
Whatever. Can you also present the screen so it appears in the recording?
Share the screen, no worries. Okay. But wait, maybe I will share just. Can I just share this site? Okay, I think I can't. It will be fine like that. Okay, so we will start with the strongly connected components, and then we'll go to the segment trees. Okay, maybe we will, leave a bit of a board so that everybody can, I don't know, write, draw anything you want, and then I will do the lesson on the right. So if you want to write something, you can just draw there. It's really fun at first, so I totally understand that you want to, play. Okay, so strongly connected components. Abbreviation is SCC, and a lot of people just use this abbreviation. So, if you ever see that, remember this is a strongly connected components. This is a graph algorithm. I've heard you've done a lot of those, so I hope there won't be any problem with graph in particulars. I will just, draw one. And we know that, wait, I will do maybe a bigger example. We know that sometimes there is a situation where, we start with one vertex, and we can go around, maybe go again to this vertex. Basically, if we ever have a situation where we can freely walk around and there is no situation where, we walk some edge and then we can't come back, then this is a strongly connected component. So, this is not really a strict definition or anything, but I believe that this will be easier to just understand that you know, if you can walk around, that means this is a strongly connected component. And for example, this on the right is not a strongly connected component, because we can see that going with this edge, we can't really go back, because all those edges kind of lead to the vertex I just colored green. So unfortunately, because here we have arrows rather than just edges, it just having, you know, a circle doesn't necessarily mean that the strongly connected component is there. What's really important to be able to distinguish them in the algorithm is that if we switch all the edges so that, you know, the ones that were pointing right would be pointing left, so like we just revert all of them. So let's say that the edge I just colored red would be right now, you know, to the other side, and the edge I just colored now would be this one, etc., etc. Then we can see that the strongly connected component is still there. Because more mathematically, if we could get to from point A to point B, reverse and from point B to point A, because this is what it means, you know, going around. We can go always from A to B, from B to A, etc., etc. Then reversing everything will mean that the path that was initially from A to B can be just changed to, you know, path from B to A. And the second path can be just changed to for a path from A to B, which means that, you know, the circling around is still there. So we're fine. And what we can also notice is that if there was any edge that was, you know, pointing towards different direction, we'll just change, you know, just change accordingly. So right, if we could go from this strongly connected component to this rose vertex, then now we can go from the rose vertex to the strongly connected component, but not vice versa, because we know that previously the vice versa was not true. So now, I mean, I've kind of messed around with vice versa thing, but if we could get from A to B in the graph at the beginning, that means that reversing everything will mean that we can go from B to A, but not from A to B. Okay. And finding the strongly connected components will base on those two observations. The algorithm is called, wait, I have it written somewhere so that you could check it out later on Wikipedia or something if you wanted to. Corsaju, I don't know how to read it, sorry. Okay, this is the name of the guy that invented the algorithm or something, and you can find it just by searching the name. And what we need to do is, firstly, we need to do the DFS from, well, any random vertex. I hope everybody can do that. And then, so let's say we have our graph as in the beginning. Let me just, you know, rewrite it. Okay, and we're just doing DFS from any random vertex. And then what is important is which vertex is, you know, the one that was left first. So I don't know if you've heard about this technique, but it's called post-ordering. Basically, what it means is that we're doing the DFS, and whenever we get to the situation where we can't go any further, then we are kind of, finishing our recursion, and we are going back to the previous vertex. So in this example, we would start here, then maybe go here, then maybe go here. Maybe we'll go here with our DFS. Okay, and we got to the situation when we can't go any further. So we're kind of going back with the recursion, and this would be the first vertex that we are leaving. So the post order of this vertex would be 1. And then maybe our DFS will go like this. And we can see that from this vertex, we can't go any further because this neighbor has been already visited. So we can just, say that the post ordering of this vertex is true, and we can leave it like that. And then our DFS will say, okay, this vertex has all of his neighbors already visited, so the post ordering will be free. And then we'll go maybe like this with DFS. So for here will be 5, here will be 6, and here will be 7. And this is the post ordering of our whole graph. You need to remember that obviously there are a few post orderings. So depends how the graph looks like, right? If this neighbor would be first before that neighbor, then we can see that this vertex would have number 1. And, all the numeration will be different then. But it doesn't really matter for most of the algorithms. Okay, and what we need to do now after the post ordering, which is not hard, it's just, writing one DFS, right? So it's just 4 or 5 lines of code. Then we need to take those post orderings and do the DFS, but on a reversed graph. So we are using the observation that we did before, that going from A to B and from B to A on the reversed graph is still valid, because we can just reverse all the paths. And on the reverse graph, we need to start with the post ordering of the biggest value. So with the 7, and let's see how it will look like on our graph. Wait, maybe I will just make it a bit smaller. Okay, I think it will be better now. Okay, so I will write our graph, but reversed. Like this. If I make any mistake, you can just, shout or something, because I can't see the chat. I think it should be fine. Okay, so we're doing DFS starting with D7, which is this one. Okay, let's see how it will look like. The only two things that we can do is go either here or here. And we'll see in a moment that it doesn't really matter. So let's just go here with our DFS. Then our DFS, the only option has to go here. Then we can only go here. And then we see that DFS can't really do anything, because we were starting with this vertex, which is already, which means it's already visited. And we can see that this edge is now reversed, which means we can't really go with it to all the other vertices. And basically, all the vertices that we visited right now is the strongly connected component of 7. This is magic, but this is how it works. And we can see that it works because from 7, in either graph, we can go to all of the strongly connected component vertices by this observation. And the edge that we went with in the first graph, which basically meant that, if we could go with this edge, and that meant that all of the vertices here would have smaller numbers, and all of the vertices here would have bigger numbers because of the post-ordering. That means that reverting the whole graph, it means that we can't go to any of those smaller post-ordering vertices. So if this edge was only one way, so like we can't go back with it, that means that going on the reverse graph first from the number 7 of post-ordering, we won't be able to go to any of the smaller post-ordering vertices in this graph. Okay, so we are saying that 6, this vertex, this vertex, and this vertex, and this vertex are all in the strongly connected component. And now what we can see is that, okay, the 6 already does have its component, so we don't have to really do the DFS thing here. 5 also, 4 also have, and now what we need to do is start the DFS from the number 3 vertex, which has not been visited here in this reverse graph yet. So we do the DFS thing, and we can see that, okay, the only thing that we can do is go from the rose vertex to the blue one, but the blue one does already have the component. So we don't really want to do that. We don't want to visit everything twice, because if some vertex already does have component, then obviously we don't want to, say that it's in a different one, because that would not be true. And what we can do now is just finish this DFS and go further. So we can see that 2 has not been visited yet, and we can start our DFS from here, and we can see that we can't go really anywhere, because the only edge going from this green one is to the rose one, which already is a strongly connected component by itself. And then what we can do is just, do the last DFS. And those DFSs, how many times we have to make a new DFS, because for the 6, for example, we didn't have to do another DFS. So how many times we had to do DFS means how many strongly connected components we have. And this is basically the whole algorithm. So as you can probably see, it's not hard to write. It's just 2 DFSs. The harder part is, why does it work? And basically, it works because of those 2 observations that we did at the beginning. The only thing I would like to mention, I haven't mentioned before, and it's quite crucial, is that remember that doing the DFS from any random vertex doesn't always mean that you will visit all of the vertices in the first graph, because for us, luckily, we started with 7, and that meant we visited the whole graph and we were happy. But there may be situations when randomly, for example, we will start with this one, right? And that would mean that our DFS will visit 2, will visit 1, and then we'll basically finish because we can't go, from 3 to 6. And what we need to do is still visit the whole graph. So the first DFS would give numbers 1, 2, 3, and then we would need to start, and our DFS with any of the other vertices that we haven't visited yet. Okay, and I think that's it for the whole algorithm. Just first DFS. Okay, maybe I shouldn't write yellow because we can't see anything with yellow. First DFS from, but we need to visit all vertices. Then we reverse the edges, reverse edges, and then we do DFS from largest post order. And that's it. I think I froze for a minute. Can you hear me well now? Okay, perfect. Can you please raise hands or do the thumb ups if you understood the strongly connected components? Okay, perfect. I see a lot of thumbs up. I'm happy about this. So let's do the task, for example, because, okay, fun. The algorithm is easy, but why are we doing this? So let's say that we have a graph. Task. We have a graph, and what we want to do is count how many paths are there from some point A to some point B. So maybe we have a graph like this, and we want to count the number of possibilities to go from A to B. And I will leave you for a few minutes to think about this. And then in, I don't know, 3-4 minutes, I will give you a clue. If you have any questions in the meantime, obviously you can just write them on the chat, or also, I don't know, just shout, ask. Maybe I will just explain quickly here what options do we have. So we can, for example, choose a path like this, or I don't know, we can go like this also, but we can firstly go left. So for example, take this path. And we can take, I don't know, this path. So overall it will be 1, 2, 3, 4, 5. I think it should be 5. I'm not sure though. Somebody asked a question, no STC. Well, there might be STC somewhere. I don't know, maybe, here there is some strongly connected components. And yes, that's basically a really good observation. And you should see what happens if there are strongly connected components somewhere, and what happens if there are none. So if you know how to do the task, then you can indicate it here. I don't know, maybe you do some plus or a heart or anything. But this will be our basically a place to flex if you know how to do it. Okay, so maybe let's see together what happens if we Sorry, I think the connection broke again for a moment. I'm not sure. It should be fine now though. Okay, so let's say that we can see that here we don't have any, right? Because if we go here, then we can't really go back. But let's see what happens if we had have some strongly connected component on our way. So maybe, we will have a cycle here. That basically means that we can either, go from A to B just with this pink line, or for example, we can, do one circle and then go to B. We can do 2 circles and go to B. Basically, we can do as many circles as we want. So that means that there are infinitely many possibilities, right? Yes, the path that would just, go through one circle is different from the path that would go through the circle few times. So if we do have any strongly connected component on our way, that means that there are basically infinitely many options. So now I let you think for a moment what happens if we don't have any strongly connected components at all in our graph. And maybe then we'll be able to, connect the first and the second part so that we'll get the answer for the whole task. And if you at any moment figure it out, then please flex and indicate this here. Yes, we have one person that already knows. Perfect. Yay, more. Yay, a heart. Perfect. I'm proud of you guys. Okay, so maybe let's go to solution. Now that so many people know how to do this. So if we don't have any strongly connected components, that means that the graph is a DAG. Which means directed acyclic graph, I think. So it basically just means that we don't have any cycles. So we obviously can't have any strongly connected components if we don't have any cycles, right? Because in order to have a component, we need to go around. So not having any cycles means that there are no SCC. And if we have a DAG, then the first thing I would do thinking about such tasks is dynamic programming, because going around such a graph is really easy, because we already know what kind of ordering the vertices need to have in order to have something that makes sense, right? I mean, we really shouldn't look first at those vertices, because we do have some other vertices beforehand that should be first taken into account. So if we have a DAG, that basically means that we can do, for example, topological sorting, and that would mean that this vertex would be looked at first, then this vertex would be looked at, or this one. It doesn't really matter, just like with the DFS, we can do either first. So let's say this is the third one, this is the fourth one, the fifth one, the sixth one, the seventh one, the eighth, ninth, and 10th. Okay, and we can see that okay, this yellow is really bad. Okay, I think it should be a bit better now. So, and we can see that if we already know how many ways are there to get into this vertex, and I mean the 9th one, and if we know how many ways are there to get into the 7th one, that means that going in, and the 5th one, that means that going into the 10th one, it's just all the options from the 9th, all the options from the 7th, and all the options from the 5th. Because in D, A, G, we know that if we can go from 5 to 10, and if we can go from 9 to 10, and the ordering is such that, you know, it doesn't really matter which one is first, that means that there is no option of going, you know, to the 10th and then to the 5th, because that would mean that we have a cycle, and that wouldn't be at the AG then. So all these options are, you know, different ones. I mean, going into the 9th one means that we won't go into the 7th one. So we can just sum up all the options from the 9th, 7th, and 5th. And reviewing all the vertices in such an order, the topological one, would mean, I will just write it, the topological, would mean that we can just count the number of paths such that, you know, there is one way to go into the first one, and then there is one way to go into the second one, because we can just come from the first one, and then to the third one there is also one option, then to the fourth there's one option, to the fifth there's one option, to the eighth there's one option, because we can just come from the third one, the ninth one, to the sixth one, and to the seventh one. But for the 10th, we can go either of the three. We can come from the 9, which is one option, we can come from the 7, or we can come from the 5th one. So kind of dynamic programming, but instead of going throughout the table from 1 to n, we're just going using topological order through the whole graph and looking at the vertices in such an order that we can just sum up, you know, from all the neighbors, incoming neighbors, all the paths. Okay, so let's, you know, connect the first and the second case. So an amazing thing with the strongly connected components is that if we do connect all the strongly connected things in a component, so that would mean that, you know, from the 4 blue vertices here, we'll just make one really large blue vertex. And if we do so, then we'll get a DAG. So it might be quite useful in some tasks. Remember about this trick that we can just, you know, make a one big blue vertex out of a strongly connected component. And in doing so, if we indicate that this is a strongly connected component of size bigger than 1, then we can just do this dynamic programming and, you know, see if firstly how many paths there are, but if we you know, on our way, if we see any strongly connected component of size bigger than 1, then we indicate that let's say that, I don't know, this one is the blue one, we can just say, okay, if this was the strongly connected component of size bigger than 1, that means that there are infinitely many options to go around here. So, that would mean that going to here will just sum up everything from our incoming neighbors, which is now in infinity. And here it will be infinity. And here and here, which basically means that for the 10th one, we'll just sum up infinity, infinity, and 1, which is obviously infinity. And in such a way, we can indicate that if on our way we have seen any strongly connected component of size bigger than 1, then the answer will be infinity. But in any other case, so in a DAG one, we will just get, a normal number. Why am I doing this, so around not just checking if there are any strongly connected components? Well, that's really important here, because see that if we are asking how many ways are there to go from 1 to 10, from 1 to 10, and we have a strongly connected component like not on our way. So let's say that we have a strongly connected component here and we don't have any other strongly connected components, then it doesn't really matter because it's not on our way. You can see that going into this strongly connected component, we can't go back again to 10. So what I mean is only the strongly connected SCC that are on our way are the ones that are important for us. And this is a really important trap that many people, get into. So remember that you can't just check if there is any SCC in our graph. You need to, in particular, check whether you have any SCC on your way. And you can do that with DP. I mean, there are many other options, but I think this will be the easiest one to code. Okay, that's it about strongly connected components from me. Do you have any questions? I don't see any. I believe that's good or bad, because that means that either everybody understands or nobody understands. Okay, if you have any questions, like throughout the whole lecture, maybe afterwards you can just ask them, even if it was about something that was, I don't know, an hour ago. Okay. It's not a long topic, and basically I haven't seen it so many times, but the trick with connecting a few vertices together and, having a DAG is quite an important trick. So this is, I would say, the place that I've seen it the most often. Okay, and what we'll do now is the segment trees. I really shouldn't use yellow. I was told that you've already done some basic segment trees, but I have a few tasks from the Polish Olympiads that are probably a bit harder. So we will do a quick recap, and then we will go to all of the tricks that you will need. Okay, so a basic segment tree. If we have a problem where, we have a sequence, let's say we have a sequence of numbers 2, 4, 7, 8, I don't know, 7, 8, 1, and 2. And we are asking about a sum over some subsequence. Let's say we have a query from A to B, such that A is 2, B is 4. Then we have a query like this. Maybe we have a query like this. We can use, for example, the prefix sums, right? Sums. But what if we not only have queries, but also some changes on our sequence? That would mean that the prefix sums are not really useful anymore, because changing any number, like if we change this 7, for example, for 3, that means that all the prefix sums from this place onwards need to be changed also, right? So now for any change, I will need to go through the whole sequence from this place onwards, but obviously maybe we're just changing those 3. That would mean that we're always going through almost the whole sequence, and we need to change all the prefix sums. That might be quite long, because this is of the complexity O of n squared, which is obviously quite large. So what we can do is we can use the segment trees. So if we have a sequence of size 8, then we will build a really beautiful tree over it, which would look like this. Okay, I can't count. I've done 10 instead of 8. Okay, and this vertex would store an information just like prefix sums, but for the whole sequence. This guy would store the prefix sum over those 4. This would store the prefix sum over those 2. But we also have some, additional ones. So, for example, this guy stores information about the last 4. As you can see from the drawing, basically any vertex is storing information about everything that is underneath it. So if this is our original sequence, so this is 2, 4, 7, 8, 7, 8, 1, 2, then this guy would store the sum of those 2, which is 6. This guy would store the sum of those 2, which is 15, and etc. here. And this would store the information about the whole all 4 below him, which is 18. And we can see that this is a sum of the 2 underneath. 21, and now a really hard math. I think it's 39. But I don't have as many fingers to, properly add those 2 big numbers. Okay, and now changing one number, we can see that it will only change all the information in the vertexes above us. So it will change this one, and this one, and this one. So if we change 7 for 3, that means that 15 will be changed for 11, 21 would be changed for 18, and now 39 for 36. And as you probably know, such tree is of height logarithm of n. Logarithm means basically that, if we're dividing n by 2 by 2 by 2 by 2, how many such steps we would do in order to get to 1. And we can see that each time we're kind of dividing our not of the tree by 2. So 39 is the whole sequence, but 21 is over the first 4, and 18 is over the last 4. Okay, and how we do the queries on such thing is that we have, we have this one knot that is in charge of everything, and we're asking him whether he does have the whole information. Let's say that our query is now about from 2 up to the 6th entry in the sequence, and we're asking Bob, let's say this is Bob, hey, can you give us the information about everything between 2 and 6th entry, 2nd and 6th entry? And he can say no, but because I also have information about the knots that don't really concern you, but I can ask my children. And we are asking Bob's child. I'm sorry, I have to remove this art because I need more space downwards. And we will ask, Bob will ask his child, okay, do you have all the information? And the child will say, I have all the information about everything from 1 to 4, which means I'm also having things that don't really concern you, but I will ask my children. And we are basically asking, the left child, okay, do you have all the information? And the left child will say, no, but I will ask my children. And the left knot will say, no, I don't have information that concerns you, which, is because the query doesn't really overlap with 1, which are the vertices that this knot is having control over. But the vertex 2 will have all the information we need, right? Because 2 is 100% overlapping with the query, which means we are getting the information from here, and we need to continue because 1-4 was asking not only his left child but also his right child, right? So the right child is having all the information stored about the vertices 3-4, which means that it's overlapping with our question, and we can just take all the information. And we're doing the same further here. Okay, and I'm sure you've done this. It's just a quick recap because we'll be using this a lot today, and I want everybody to be on board with everything I'm saying. The question is whether you know why is it working quickly, because we're going down the tree and we are basically asking all the knots, and a lot of them are asking their children, and the question is why we are not really going through the whole tree. Why is it fast? So maybe I will make it a bit smaller. Just a moment, sorry. Okay, it will be easier to look at now. Okay, so why is it fast? There are 2 options of the queries. First is that, let's just draw a tree first, maybe. The first option is that, the whole query will be in one of the children. So, for example, like this. And now we see that the right children doesn't really have any information. So what we will do is we'll just, go into the next level and basically do the same. So only one of the children does have information. We'll just need to recursively go into the first child. We don't need to go into the second one. That would basically mean that, we're doing the same, just the level below, So it's fast, right? Because there are only logarithm of levels. So that's fine. The second option is that our query is contained in both of the children, not just one. So such query would, for example, look like this, right? And what does it mean is that for this child, all the queries now, I mean, this was the whole query, but only the left part is something that concerns left child, right? And we can see that now all of the queries are kind of up to the end of the of this child's of the notes that this child is taking care of, which basically means that his right side will always be something. His right side, I mean his right child, will be always the one that does have all the information about the query. So we will need to go further, just down with the recursion to the left child, and the right child will just give us the information. And later on, we do have the same, basically the same situation with the left child. So we know that the right child of our left child will have the information about the whole query, but the left one will have either zero information or be in the same situation as this one at the beginning. So each time we're basically either just going level down, or we're going level down on both sides, but then we know that level below that level we'll just have all the information needed on the right side, and we won't really have to go 3 levels below us into the recursion here. Okay, this wasn't really a mathematical proof or anything, but this is quite interesting. Why does it work fast? Because we will be using this quite a lot. Okay, I think that's most of the things I wanted to say from the recap. Let me just check out quickly if I've mentioned everything. Okay, yes. The only thing I want to remind you is that on the trees, we obviously can't do everything. So, for example, division or subtracting might be hard because we need the operation to be such that we can do it in not any particular order, because we need to have all the information in the right child, all the information from the left child, and we just need to combine those two information in order to get the information for the parent. So we can't use it for any operation, but basically for so many that it's very useful. Okay, and the thing is that obviously our sequence is not always of size 2 to the power of n. We may have a situation where our sequence is, I don't know, of size 5. And then we need to be able also to do a segment tree over that. So what we need also is some kind of element that would be neutral. So for example, for some, such element is 0, right? Because if we add 0, then it changes nothing. And we can just, take our sequence of size 5, 1, 2, 3, 4, 5, and then add zeros, so that it was of size 8, and we could build a segment tree over it. Or other neutral elements. For example, for multiplication, it would be 1, obviously, but then for example, for minimum, which is also a valid operation on segment trees, it would be something big, because a minimum from a and something big is always a. So we don't really want the neutral element to influence anything. That's the case. As you can probably tell, for maximum, it would be something really small. And sometimes the operations are not so obvious. You will see today tasks where they aren't. And you will need to think of this neutral element by yourself. Okay, so maybe I will give you the task now. Okay, so the task is quite hard. I mean, it doesn't really only contain the segment trees, but it's a task from, I think, 14 Polish Olympiad in informatics. I'm not sure. I will check that later, from which one it was. But it's called Megalopolis. And we'll do a slightly easier version today. If you want to check out the whole task, you can just Google it, or I can send you the links later. Okay, so let's say that we have a tree, not a segment tree, just a tree. And what we have is, we have some highways, which are, fast, so they are quite important. And let's say that highways are the green edges. And we have some, normal roads. So, for example, the rose ones would be the normal ones. And what we need to do is we need to answer many queries, such that we're asking how many highways are there from A on the path from A to B. So we can see that from A to B we have 2 highways. But so that the task wasn't too easy, the people are also building new highways. So like cities obviously progressing, and we're having more and more highways in this country. So let's say that you were given questions such that either we'll be building a highway, so an edge of number 4th, let's just enumerate those edges, and 7, 8. I will do that later. And let's say that we are changing the 8th path into the highway. And then we have a question, okay, now from A to B, how many highways do we have? And then maybe, we will change an edge 9 for a highway. And now we can see that the question from A to B would be not 2 as previously, but 3. Okay. And we have just many queries like that. Many, I mean, something around 10 to the power of 5, fifth, 5, I think 5, 10 to the power of 5 queries, and the whole tree is of size also 10 to the power of 5. Okay, and again, if you know how to do the task, then you can just indicate it here in our place to flex. And in around 5 minutes, I will try to, give you some information, some further information. I see a heart. Perfect. Yes, this is the second stage of the 14th Olympiad in informatics, which was about 15 years ago. But... Oh, and the task is translated. Amazing. I can send you the link then. And if you're bored, and if you know already how to do the task, you can just, just try to write it.
Ho messo il collegamento sul wiki. I put the link on the wiki. Sorry.
Okay. Thanks, Luca. Okay, so okay, 4 people say they know how to do the task. Amazing. So for the rest of you, I will give you a clue. So let's say that we are changing the path 9 to highway. That basically means that all of the vertices here will be given extra highway on their way to the vertex number 1, so the root. And we can basically use it because we know that I've heard that you know what LCA is. And my clue for you is to use the LCA and use the fact that, changing the path number 9 to highway means that all of those vertices are given another highway on their way to 1, to the root. I will give you a few more minutes to think about it. If you know how to do it, then just code it, I think. I don't think anybody will be able to code it in 5 minutes, so I hope you won't be bored for the next 5 minutes. Okay, so let's quickly recap how we know how to the LCA works with such tasks. So if we know, the LCA, then we exactly know how the path from A to B will go, like, right? Because it will be the path from A to LCA and from LCA to B. I think this is something you should know after the lecture about the LCA, but if you don't remember it, then just trust me. And basically, if we know how many highways are from A to 1, which is the root, if we know how many highways are from B to root, and if we know how many highways are there from LCA to root, we can basically count how many highways are from A to B, because that would mean that, all the highways from A plus all the highways from B to root minus 2 times all the highways from LCA to root. Because we are going from A to LCA, we're not going from this, but we've counted this, so we need to subtract it. And then from LCA to B, and again, highways for B also counted the the highways from LCA to 1, which also needs to be subtracted. So we need to subtract it 2 times. Okay, so if we knew how many highways are there, we could basically solve the task, right? Knowing the LCA, which is also something that you need to code, but this is not what the lecture is about. So if you don't remember how to code the LCA, you should probably recap that. And amazing. If the highways wouldn't change, then we could do it easily. I mean, we could just do one DFS and count how many highways were on our way. But unfortunately, now we also have the changes. And if you see there were sequence changes or anything changes throughout the time, you should immediately think about the segment trees. I mean, it doesn't really matter that it doesn't really mean that it's a segment tree, but it strongly indicates that probably there is a way to do this task using segment tree. And yeah, this is also the case, because if we have had some enumeration of the vertices such that we could treat them as a subtrees, it would be amazing, because it would just mean that all the vertices in such a subtree would be given +1 while changing this road for a highway. And this is a trick I've been told that you should also know, but again, I will recap that. This is a trick with pre and post orders. So pre-order is a number that a vertex is given while going for the first time to the vertex with the DFS. So let's take an example. Maybe while looking at the example, you will be reminded how it worked like. So we would basically start with this vertex, right? So it will be given a number 1. And then let's say we're going to this neighbor, because why not? And this neighbor would be given number 2. And now, while going out of the vertex, so, the case where we couldn't really go any further because we didn't have any neighbors that were not visited yet, what we would do is we would give the last pre-order number, last pre-order that was given, and write it as a second number. This is quite important because it's not really the same as a post order. So please don't mess up those two, because as you can see, the post order of this vertex would be just 1 because it was kind of left first, but we still would give the number 2 here, which is the last pre-order that was given up to that point. Let's go further to see how it works like. So it was given 2, and now our DFS will go to the next neighbor of 1, which is here, and it will be given number 3. Then we'll go here. Well, this vertex will be given number 4, and now we can't go any further, and the last pre-order number that was given was 4. So we'll just, say that this vertex has the second number of 4. And now we are visiting the next neighbor, which is 5. Next neighbor, which is 6. We're going out, so this vertex has the second number of 6, then 7, 7. And now we have something interesting, because we are leaving this vertex, and the last given pre-order number was 7, which means that the second number here would be 7. Same here, 7, right? Remember that giving the second number, we're not increasing the pre-order. We're just leaving it as it is and just giving it to this number. So remember that we're increasing only while visiting a new vertex. Okay, let's go further. Let's see. It will be 8. it will be 9, and we're leaving it with the last border given 9. We're going further, the same situation here, the same situation here. Oh, sorry, I forgot about this one. So it will be 10 here, sorry, because we're visiting this one. Situation with, going in and immediately leaving here, same here. And now we're leaving this vertex, and the last given pre-order would be 12. And here also 12. And now we've, visited all the neighbors of the one. So we are also kind of leaving it. I mean, it's the last one, but we are leaving it. And it will be given a second number of 12. And as you can see, the first number is the number of the vertex. Right? And the second number is saying, okay, in my subtree, there are all of the vertices between 1 and 12. And you can see that it really works on this example. And if you want a further explanation, basically, if we're visiting anything, in our subtree, and we're giving it all the numbers, all the pre-ordered numbers, and then we are leaving ourselves, that means that the second number would be the last pre-order number that was given in our subtree, right? Because we're just leaving the vertex if our whole subtree has been already visited. So it works like this. And now we have really valid numeration with our vertices, because we can say that, if we're changing this road per highway, that means that all the vertices between 10 and 12 will be given +1. And if we're changing this road for a highway, that means that all of the vertices between 5 and 7 will be given +1. And if we're changing this road for a highway, that means that all of the vertices between 8 and 12 will be given +1. Right? And those +1s can be indicated on a segment tree. So we can have a segment tree over all vertices on the tree. And from this segment tree, we could, just read how many highways have been up to that point for a given vertex. So in this example, with this data I gave you, we would have a segment tree of size 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We would have a segment tree that would be all zeros at the beginning. If, for example, all of the roads are normal ones, and we don't have any highways. Okay. 0, 0, 0. We know that, here we would need to have more zeros in order to kind of have the power of 2. But let's say, that we do have it. We do have zeros here, let's say. I think this should be fine. And now what we are doing is we're, adding +1 on the sequence on the subsequence 10 to 12. So what we are doing is, we're looking for a base vertices for the subsequence, which would be those, and we would add +1 in those vertices, right? And then what we would do is we would say everything from 5 to 7 is also +1. So 5 to 7, those are the basis vertices, which is also +1. And then we would say, okay, everything from 8 to 12 also does have this one. From 8 to 12, which is this one and this one. And now asking how many highways are there, from 12, for example, up to the root, we would just go up our segment tree and see how many, ones do we have on our way. So we can see that we have 1, 2, 2 ones, which means there are 2 highways on our way up to the root. And let's say, for example, that, I don't know, let's say that now we've also changed, this one. So 11 would be given an additional highway. So we would have +1 here. And now asking about 11, going up, we can see that we have 3 ones on our way. So we would add 1 on a subsequence, and then we would read how many ones are there, and the sum over the subsequence, which basically would give us the answer. Okay, as you see, this was quite a complicated task. So I hope nobody got lost. I will just try to, move everything so that it would make sense on the board. Okay, perfect. And this is the whole task. So you need to do the LCA first, then you need to do the pre-order ordering with those second numbers that would indicate, what is the range of such a subtree. And then you would need to also create a segment tree. And each time you're adding a new highway, you need to see which of the vertices are, the lower one, and then ask the lower one what is the range that this subtree is in favor of. And then every time we add a highway, we're just adding +1 on a segment tree, and then answering the queries, we would just need to see what's the number, what's the sum at the point A, what's the sum at the point B, and what's the sum at the point LCA in the range tree. So as you see, a lot of hard components, but if you test everything, if you test properly every component, then the task is not hard. You just need to have a properly tested LCA, properly tested segment tree, and properly tested last pre-order and pre-order ordering. So remember that you shouldn't just write the whole program and then hope it works, because it might be really hard to debug all 3 components, because they are quite, complex. So remember to write a pieces of code, test it, and then everything should be fine. And yes, you can send it on Dashkopu. Yes, this is how it's read in Polish. Basically, the site I've sent you, and you have a lot of other Polish Olympiad tasks there. You can change a website for the English, and then you have a task archive, and then in the task archive you have all the tasks from the Polish Olympiad, Junior Polish Olympiads, but Junior Polish one is not translated, unfortunately, so you can play with ChatGPT there, and also some other competitions. But with the Olympiad in Informatics, the new ones should be translated. I think everything from the 21st onwards is. Yes, so that's it for the task. Maybe I will ask can you, I don't know, give a thumbs up if you understood it? Okay, I see a lot of thumbs up. That's perfect. Okay, and going to the next task then. I think. Let me see if I've told you about everything here. Oh, okay. So the next task is another trick, and then we'll go to query on a subsequence and asking about the subsequence ones. So the task is, we have a bucket, and let's say that the first bucket is of volume 2, the second bucket is of volume 3, the third bucket is of volume 1, I don't know, maybe 4, etc., etc. And then, they are somewhere placed so that rain falls. Let's say that at first moment the rainfall falls from starting from here up to here and is of size 2, which means that every bucket here would be filled up of volume 2, I don't know, square centimeters to the power of 3, you know what I mean. Then maybe, so it would be of volume 2. Here the water would be of volume 2, which obviously is not something that we can do, so it would just mean that the whole bucket will be filled up, and there would be some water underneath, but it doesn't really matter. So there would be a puddle around, and then here would be the water would be also of size 2. And then let's say that rain fall on this subsequence and was of size also 2, which means that in the second moment this bucket will fill up and this bucket will overfill. There will be a bucket here, a puddle here, and this bucket will be just filled up, up to 1/3. And then maybe here the water will fall and the rain will be of size 3, which means that this bucket will overfill in the third moment of time. 3 will be overfilled. And the question is, tell at the end at which moment each bucket will be overfilled. So like the first moment that the bucket will, fill up. The answer here would be never for this one, never for this one. The first moment for this one, because the first rain, it's already overfilled. The second rain for here, because it will be filled up after the second rain. Then never for here. Then the second moment for here, because we can see that the first rain didn't do anything with this bucket because it was just from, the second up to the fourth one. And for this one, the answer will be never, and for this one, the answer will be 3. Okay, and that's the task. If you know how to do it, then again, flex, place. If you know how to do it, then, heart, anything you want. Somebody asked if this can also be done with a segment tree on the Euler walk. Can you elaborate what you mean?
That was for the previous problem.
Oh, okay. For this one, right?
I mean, no. For the problem on the tree.
Okay. And what about the last question? Is it about the megalopolis task? Okay, and you want to, you're asking if the last task can be done in O of log n. I mean, each query is unset in log n. Because what we are doing for each task is either we are just, either we're just asking the segment tree, and each segment tree query would be the log of n. And also we need to ask the LCA. What's the LCA? Which would be another logarithm. So we'll do the logarithm of LCA and the logarithm of segment tree, which is logarithm times 3. And for that road change, what we need to do is just do the change on the segment tree, which is also of logarithm of n. Because the pre-order numbers and the jump pointers from the LCA, everything will be done beforehand. So I'm not sure what's the question about. The bucket one. Okay, sorry. Can it be done? The queries are at the end. It's not that at each time we're asking about something. It's just that after all of the ranks, we need to tell when was the particular bucket filled. And yes, it needs to be done in a logarithm tasks time. So the size of the sequence will be around 10 to the power of 6. So here, this would be the output. And the queries would like this. 3 ranks. First would be from second to third buckets of size 2. Then would be from fourth up to 6 of size 2, and then it would be from 8 to 8 of size 3. And we obviously also need to have all the buckets on the input at the input. So let's say that we have all the rains first, and then we also have 8 buckets, and the buckets are of size 2, 3, 1, 4, 6, 1, 1, 2. And we all the data, all the rains, number of rains and number of buckets can be both up to 10 to the power of 6. Does it answer your question? Yes, that's basically the answer. I am doing this from the other side, like adding and seeing if it's 0, but that's basically the same answer. Please don't look at the chat if you haven't figured it out yet. And if you want to figure it out by yourself. But yes, now you can place a heart or something in, I know, rectangle. Yes, that's true, but I don't think there is an option without amortizing. I will think about this while you're thinking about the task. But to be honest, I think there was a similar task on a Polish Olympiad in informatics. It was the 21st one, so 8 years ago. But it was a one with online queries, so I didn't want to give it here. But basically all the solutions were so I don't think there is one. I mean, we can never be sure. But... Okay, I will give you one clue about the task. So the important thing is that if some bucket was overfilled, then it will be overfilled forever. I know it's obvious, but it is really important. Like, we don't have to take it into account anymore. So maybe if it was overfilled, we can just throw it out, at some particular moments. The question for you is how to know that some bucket has been overfilled. And this is the first question you should answer by yourself. If I have the reins and I'm simulating them, then how to know that some bucket has already been filled up. Okay, I will give you a clue again. So now we want to answer that question. How to know that a bucket has been already filled up? Any buckets. Like, we're just going with the rains, simulating them, and at some point we know that some bucket has been filled up. How to do that? Basically, we can have, for example, a segment tree that would tell us how much rain would it need to fall in order to, have the in order to have all of the buckets. How much rain would it need to fall in order to fill up the buckets? So let's say that here, we would have a segment tree of 2, 3, 1, 4, 6, 1, 1, 2. And then what we need to do is we would just, with each rain, for example, with the first one falling from the bucket 2 up to the bucket 4, we would say, okay, we are subtracting 2 from the whole range. So, here it would need to be 5. Here it would need to be 5. Here it would need to be 6. And here it would be not a sum, a minimum. I will tell you in a moment why. 6, 1, and 1, 2. So 1. Here it would be 1. Here it would be 1. Here it would be 1. Okay, so we have a segment tree. I wrote it the other way. It doesn't really matter. So we have a segment tree of the minimum. And now we can see that if we say, okay, from the moment 2 up to the moment 4, from the bucket 2 up to the bucket 4, we need to, subtract 2, right? Because this is how all the values will change. Each one would be of 2 smaller after the rain, because if at first I had a volume of 3 to fill up, then after the rain that would fill up 2, we would need just 1 volume to fill it up. So what we can do is we would find the base and we would say, okay, if this is the minimum, then we know that the minimum will be of 2 smaller, right? So we need to subtract 2 from the minimum. Minus 2. So the minimum here will be now 2. And obviously we need to also actualize the everything from that point upwards, which is not upwards on my drawing, unfortunately. So we would need to say, okay, this is 1 from now on, this is also 1 from now on, this is minus 1 from now on, this is my minimum of 1 and minus 1, which is minus 1, and this is minus 1. Okay, and that means that, if this value is non-positive, that means that some bucket here has been filled up, right? So, maybe we can use that information and, as I said before, just not count this bucket anymore. I will leave you for a moment with that information, and in the meantime I will, draw the segment tree from upwards to downwards. Okay, maybe I will tell you a bit further about this tree, because this is a kind of magical tree that we're changing. We're having minimas, right? And we're changing a subsequences because we're, subtracting -2 on a subsequence, not in in a particular for a particular bucket, but rather for the whole subsequence of buckets. And then we need to ask about, -1 on the whole um, the whole sequence. So, okay, we can see that getting the minimum is easy, but what about those two? I mean, those two don't know yet that they need to be changed, right? And the idea is to do that later. So we don't really need to worry about this yet. So maybe, we can do that later. And that would mean that we can still keep our logarithmic complexity. And maybe the problem will be solved by itself later, just like with the normal segment trees. The thing is that, we need to remember how this -1 word is, because the idea will be to kind of throw out the bucket that was filled up. So if we have -1 in the root, so if the value here is non-positive, then we will go down our segment tree and just throw out this bucket. Say, okay, this is the first moment that this bucket was either filled up or even overfilled, and we don't really want to take it into account anymore. So we're checking. The root is non-positive. So we see that, it was the value that was took from the left side, from the left child. And same question here. It was taken from the right side. And we can see that, this -1 is neither taken from the left side nor from the right one. So what we can do here is just store information that, we subtracted to. So we will not only store the information, what is the actual value right now, but also what was the value that was subtracted. And then if we see that, the children have not been changed yet, then, and we are going down, I mean, we're passing by this value, and we're asking children, okay, which of you is the bucket that was filled up? Then we are kind of just pushing the value downwards. We will see this trick more later with the sum, with the XOR, with many other operations. Now let's just, walk around this idea, and maybe it will be more clear later with easier tasks. But keep that in mind, that we need to, indicate to the children that they need to be changed. And if they are changed, so this would be -1 and this would be 2, because we're passing by this value anyways. So we can just, say to the children, hey, please change yourself. Here. And we see that this is the -1, which is the value that, the bucket that was overfilled. And we can say, okay, so at first moment, the third bucket was overfilled. And we can kind of throw it out, which would mean, okay, this bucket is not here anymore. So it will be some, value infinity that can never be overfilled, because it's just something that doesn't interest us anymore. We don't want it to be indicated again that it was overfilled, and we never want to look at this bucket again. We're just throwing it out. So we're putting some really big value here. And then, we need to again actualize the path above us. So we need to say, okay, this will be from now on 2. This will be from now on 1, because this is just a minimum of those 2. And this will be also 1. And now we see that the value in the root is positive, so we don't have any other bucket that would be overfilled. And we can just simulate it further. So we can see that the second range is for the buckets from 4th up to 6th. So what we need to do is we need to subtract -2 on such a subsequence. So what we do is we're trying to find the basis knots of the tree, which we're doing with the standard, procedure. And then we subtract -2. And we need to remember 2 things. -2 for the children, so the value that we will push if we ever go downwards, and a second value of what would be our value right now. So this is the value. Maybe I will, write it with different color. I think it will be easier that way. So this is the value for the children, -2 to add -2 to them, and then -1, which will be the actual value of the minimum right here. And we need to, also change this one for 0. And this one doesn't have any children, so we don't need to remember the value to push. We can, because, if we ever go through that value, we'll try to push -2 to the children that don't exist. So depends which way is easier for you to code, but basically we just need to, subtract 2. So indicate that the value from now on is just 0. Here will be just 0. Here will be -1. And here will be -1. And again, we can see that the value here is non-positive. So there has been a bucket that has been overfilled, and we need to find it. So -1, the value came from the right child. -1, the value came from the left child. And now we can see that we have a value here to push the children. So we are pushing the value, saying that, okay, each of the children is of volume 2 smaller. And we can see that this was the left child. So we are saying, okay, in a moment of 2, the bucket number 6 was overfilled. And again, we do the procedure. Okay, this value was already pushed, so we can just forget about this. And this bucket is something that we don't want to take into account anymore. So, everything up will be again changed. But in this situation, we can see that the value in the root is still non-positive. So that means that there's another bucket that we need to find. And basically, this value 0 came from the left side. This from the right side here, and from the right side here. So this is the bucket that has been overfilled. We need to remember that it was the bucket number 4, and we need to not take it into account anymore. So it will be infinity, infinity, 1, and here it will be 1, which means that, the value is positive, so we don't have to take it into account anymore. And this is the whole task. It works quickly because each bucket can be taken from the segment tree only once. So we'll do the magic operation of, going down the tree and taking, throwing out the bucket just n times. So we have, just a moment. Yeah, we have complexity of n log n from this operation. And then for each rain, let's say that the number of rains is m, we are, just going down the tree and just going down the tree and changing the minimus. And we can see that the operation of pushing something to the children don't really indicate any new component of the complexity, because we are just doing this on the way. And you will see a lot more about this in the next tasks. So don't worry if you haven't catch up the idea yet. We will talk about this more in the next tasks, and maybe then you can come back to this task and try to understand it again. The idea that is important that I want you to understand now is the taking out the buckets. So the trick that, if we have a non-positive value here, then we are kind of just throwing out the buckets, and we are not taking it into account anymore, indicating some really large infinity value in our segment tree and saying, okay, this bucket was at this moment filled up. And, at the end, we just kind of, at the output, we just put those values that we remembered on our way. Okay, who understands the idea with taking out the buckets? Please, thumbs up. Okay, I see some thumbs up. That's perfect. If you have any additional questions, you can just, ask afterwards, always. Or in the meantime also. Okay, are there any questions? Somebody's asked about the complexity. I hope I've covered this now. Is it clear now? Why does it work fast? If no, please let me know. Okay, and we'll go further to the idea of pushing down information to the children. Just maybe we could do a little break, because we've been having the classes for the past 2 hours, and probably you want to have tea if you're thinking all the time. Maybe you've made some breaks by yourself, but I think it would be nice that you could, get up and walk around for 10 minutes. So yes, let's meet up again in 10 minutes. So at 5:25, I will make myself more tea also, and we'll get back to the idea of information. See you in 10 minutes.
10 minutes, starting now.
Okay, I'm back. I hope everybody is back too. If not, I will just repeat the task, I guess. Okay, so I told you I want to tell you more about this pushing down the information. So maybe let's go to the basic problem. I think you'll see clearer then how it looks like. So let's say we have a sequence of numbers. 1, 4, 3, 2. I don't know. Y, 4, 4, 2. I don't have. Okay, perfect. And let's say now I am having I'm adding or subtracting on a subsequence. So let's say, I'm adding +2 to all of those numbers. I'm adding +4 to all of those numbers. And the question would be just about a sum on some different subsequence. So, we have a queries like that. Either we're adding from A to B value X, or we are asking about some subsequence, about the sum of some subsequence. So here, for example, we would say, okay, +2 to all of those, +4 to all of those. And then we could, for example, have a question. What is the sum of those three? And we would say, of course, it would be 2, which we added 2 to, so 4. Then 1, which we added 2 to and 4 to, so 7. 4 plus 7 is 11. And then for that, we added 4 to, so the sum would be 19. Okay, that's the task. And let's see why, the approach from the normal segment tree wouldn't work. So let's say we're having those numbers and we have just a tree of sums, which is something we've done with, normal sequence trees. So we are doing the same here. 10, then here we would have 8, and then here we would have 18. Okay. And let's say that we've added, +2 to all of those numbers. So it would mean that, we're looking for the base vertices. Those are the base vertices, and we're just adding 2 to them. So 2 obviously times the number of the number of the numbers that are that is this vertex in charge of. So, if we added +2 to all of those 4, then we would need to add +2 times 4 to this sum, right? I think this is something logical. And we would need to add +2 times 2 to this number, because it's in charge of 2 numbers and we are adding +2 to both of them. Okay, and now let's say we have a query that would ask us, okay, and now what's the sum of the subsequence 5, 6? So that would be those 2 numbers. We would again just look for, the base vertex, and we can see that this is the base vertex. And we would ask, okay, so what's the sum? And this vertex would tell us 5. And we can see that that's not the case, because we've added +2 to all of those 4 numbers. But, we've only changed +2 to this base vertex of those 4 numbers. And the problem is that this child doesn't have the information from the parent. So that's something we need to, fix. And the idea is the same as with the bucket. That's why I told you that this is not something that you need to understand now. We'll talk about this later. So every time we go from the parent to his children, so every time we're visiting any of his children, we would have an additional information that we would just push down. So here, we would not only say, okay, so, we're adding +2 to all of the 4 children, but we would also say, okay, and if any time we go to the children, we need to add 2 to all of them. So we're basically just, having those 2 information. Something is loading. I don't think that's something I should be worried about. Okay, so let's say that we have, to either a segment tree of 2 values or 2 segment trees or some structure that would, indicate the node of the segment tree. It depends how you prefer to code it. But remember to always store those 2 information. So the actual sum and also an information to push down whenever we go to the children. So how it would look like here. We would say, okay, so the first query would be adding from 3rd to the 7th 8th vertex. I can't count, I think. Okay, from 3rd to 8th vertex, the value 2. And then what we do is, let's say, ask about maybe something more interesting than this. Maybe we'll go further down. So we would just ask about the vertex number 6. So from 6 to 6, what's the sum? And we can do this the same as we would do any normal range tree. We just start from the roots and then we ask the children. So the left children, hey, can you give me the information that I need? And the left children would say, no, I'm in charge of all the vertexes between 1 and 4, and you've asked about the 6th one. I have no information that you need. Please leave me alone. That maybe the child wants to play games or something. Okay, so the father would ask the right child then. Okay, the left child didn't give me any information. Can you give me the information? And this child would say yes, but unfortunately, I don't have the information. I need to ask my children. And we can see that we have 2 things here, as we said before. So we have a thing that we need to push down. So the +2 that we need to push to all children. And we have also a value 8 plus 2 times 4. So it would be, just, we would change this value 8 to 16. So if we see that we're in a knot that does have this information to push down, then we are doing it. So, we would say to the left child, let's, change you. So the change would be 5 plus the number of children that he's in charge of. So 2 times the value 2. So this would be the value 9 now. And also, please remember that, you might also have children. And these children might also need this information. So not only change yourself, but remember to later on change your children. So this would be the second value. And the same with the right child. So, we know that this value would be changed by 2 times 2. So plus 2 times 2, which would be 3 plus 2 times 2 is 7. And then we would also need to remember the value that our children might need in the future. So +2 to the children. And we've already pushed this value. We don't need it anymore. We want to erase it. Maybe I won't erase it like this so that you actually remember that the value was there, but rather just, cross it out. We don't need it anymore. It shall be 0 now, because we don't have anything to push down. We've already done that. We don't want to do it twice, right? Because if we do the query and then we would do this query again for some reason, or maybe different query like 5, we would go through this not again. And we can see that going through this again and not erasing previously this information will lead to, adding this +2 times 2 twice. And we don't want to do this. Okay, so we've pushed the information. Now we can recursively go to our children. So we would ask the left children, hey, do you have the information I need? And the child will say, yes, but I also have the information that you don't need. So I need to ask my children. And he will, what he'll do beforehand, asking the children, is push this +2 down. So it would be 1 plus 2 times 1, so just +2, and 4 plus 2 times 1, which is just +2. And now we can erase this information to push down, because we've already done that. We don't want to do it twice. So, we're just saying, okay, we've pushed this. We don't have anything to push down more, so that's okay. And then recursively going to children, the left child will tell us, no, I don't have anything to units. And we will go to the right child, which will be like, yes, I have all the information you need, which is 4 plus 2, which is the value that it has to remember. Again, this +2 would be also indicated here, but because those are, the leaves, so like this is the last level, we don't have any children that we can push information to, then it can be here. It doesn't have to be here. Depends how you code it. So yes, we have all the information. 6 is the answer. And, we are going further. So this will say, okay, my children, and this vertex will say, okay, my children, left didn't give me any information, so that's 0, and the right gave me the information 6. Let's go check what's previously. So the 8, not 8, 16, but this vertex would say, okay, I've asked the left child. The left child collected the information and said it's 6, but I should probably ask the right child if he does have any information I need. And this child doesn't have any information, so we're not, going further. We're not asking the children, so we don't push the information. We're just pushing the information whenever we go to the children, because we don't want to do the work that is not necessary right now. Maybe we will never visit those children. Maybe, they will be left alone and we will never have to push down this information. So why would we need to do it now when we can just, be lazy? So the right child didn't have any information. So this vertex would collect the information. Okay, 6 plus 0, it's just 6. And, we can go back recursively. The left, I don't know if you still remember, it was a long time ago, but the left child did say, I don't have any information, and the right child did collect the information, 6. So that's the whole answer. I hope you understood more or less the idea now of pushing down the information. The thing you need to remember is, firstly, indicate both informations. So we need to store info. So we need to store the sum of the current vertex, so the sum of all the children or grandchildren, basically just all the base vertices that he's in charge of, and also the info to push down. So info, push, and also the current sum in the vertex. And every time we're going down to the children, so every time we're visiting children, we just need to push down the information. And also tell the children that in the future they may need to push down the information. Okay. And let's just also quickly look at how it would look like if, you know, the information would stack up. So, you know, maybe we add, okay, I will just write a new tree because this one is really messy now. So let's say we have 18 here, 10, 8. So we're just starting from the beginning, but, you know, a bit more advanced, I would say, example is, what's here, 3, is when we stack up the information. So, for example, we're adding from 3 to 8, 2, and then immediately we're also adding from 3 to 8, 3. What would happen then? 3 and then 1, 4, 2, and 1. Okay, perfect. And now we will have query such that we're adding from 3 to 8, 2, and then immediately also 3. So the first query, we would find the basis vertices, which are this vertex and this one. And as you, I hope, remember, we need to actualize the two information. So first we need to actualize the actual sum. We are doing the first query now. So, you know, it's 8 plus 4 times 2, because this is the new sum of this subsequence. So it would be 4 times 2 is 8, so 16. And also an info that in the future we may need to, you know, add +2 to our children. And the same here. In the future we may need to add +2 to our children, and then also this sum changes to 9. Okay, but then instead of, you know, asking, pushing the information, we have another query, which is basically the same one, but, you know, that may be something different. That may be 5 to 8, and that would still be the situation. So it's not only in case where two queries are asking for exactly the same subsequence. It may be also the case where we're adding from 5 to 8 another 4, and again the information would stack up in this vertex. So let's do that. We would again find, you know, basis vertices, which is this one and this one, and we would again add something to the sum. So 16 would be higher by 3 times 4, which is 12. So the actual sum now would be 28. And then, you know, we are not adding +2 to the children. We are adding +2 and also +3. So +2 + 3 to the children, which is 5. So this information kind of, you know, we're stacking one information on the other information. And we can see that with the addition, with the multiplication, with all minimum, we can always kind of stack up this information, and this is important in the segment trees, that we could do that with the information. And also, this is the basis vertex, so we need to add 3 times 2, because there are 2 vertices. To each it will be added 3, so overall to this vertex it will be added 6. So the actual sum of this subsequence will be now 15, and we need to stack up the information. So +2 + 3 is 5. And then, we may have a query adding 5 from 5 to 8, the value 4, and we would need to indicate it. So we would find the basis vertex and then change it again, the same as we were changing it before. So we would add 4 to all of the vertices down this vertex is in charge of. So we would now need to add 4 times 4 to the sum, which is 28 plus 16, which is really high number. 44, I think. Yeah, maybe, probably. And then we would need to also say, okay, and if we ever go, down to the children, we need to not at 5, but at 9. And this is not changed, because this is not something that is influenced by this query. Okay, and let's say that we now have, a question about, I don't know, maybe the 7th vertex. And now we need to do the fun that we did before. So we need to, again, find the basis vertexes of this query. But in the meantime, while, visiting some vertex while going down, we need to see if it doesn't by any chance store this information to push. So here, the left is not something that we are concerned about, but the right is. And we can see that the right does have the information that needs to be pushed down, and we are going actually to the children, because this is something that not only stores the information about 7, but also about 6, 8, 9. There is no 9th vertex, but you know what I mean. And it means that we need to go to the children. So going through this vertex, we need to push down the information. So we're saying, okay, we are pushing down 9. 5 plus 9 times 2 is 23, right? I think. So the sum would be now 23, and in the future we need to also add 9 to our children. So we're doing that, and we're doing that to the left, right one, sorry. So we're adding 9 plus 2 to 3, which is 21. And we're saying, okay, in the future, we may need to push down the information about 9. And now this information has been already used up. So the children have been informed that they need to be added 9 to. And this information is no longer valid, so we can just erase it and say, okay, now we don't have any information to push down because we've already done it. And now we can see that the left child is not something that we are concerned about, because he doesn't have any information we need, because we need information about the vertex 7. So it means that, we are just leaving this value here, and we're not pushing it forward. We're just leaving it, and maybe in the future it will be needed, maybe not, we'll see. And we're going right. And now we're going right, and we need to ask the children, because this vertex is not only responsible for the vertex number 7, but also for the vertex number 8. So we need to go further down. So going further down means we need to push this information. So we're pushing it, adding to 2, 9 times 1, because this vertex is just, in charge of this one vertex. So just adding plus 9 times 1 and saying, okay, for the children, we need to, add 9, which is not something that we are concerned about because this vertex doesn't have any children, but let's just leave it. And then, because it will be easier like that to code. You see, we never go to the children of this vertex because we never have to, because it doesn't have any children. So, this value will be just always here. And then we need to also actualize the right one. So it will be the sum of 10 and the 9 to push down to his children. And this 9 have already been pushed. We don't need it anymore. We can just erase it. This is not something we don't want to double it. So we're just leaving it up. And that's basically the whole idea of the segment tree, that we are having the queries on the subsequences and we are changing the subsequences. So yeah.
In this way, you didn't really change the parents node. So, for example, if some other queries you ask the sum from the beginning to the end, in this way.
Yeah, sorry, I forgot to mention about this. You're right. Thank you. The changing of the parents, you're doing the same as in the normal segment tree. So every time you're going backwards in the recursion, you need to again collect the information from the from your children. So if we're changing, let's go back to the first query. I will just copy this, I think. Okay, it doesn't work, unfortunately. Oh yes, perfect. Let's go back to the first query. So let's say we only have this. And it was the moment where we didn't have any of those. Okay, that was not a really good idea. We had 16 here, right? And then we need to write all of the values as previously. So here it will be 3, here it will be 2, here it will be 1. And here we have the information that we need to, we have a sum of 16 and we need to push down 2, right? I think so. That's 2. Okay, and then we need to, this is another basis vertex, and we need to add +2 here, and the actual sum now for this vertex is 5 plus 4, which is 9. Okay, so 8 turns into 16, and 5 turns into 9, and now the same as with the same as with the normal segment trees. Every time we're going back, so like for trying to find the basis vertex, we'll go here, then we'll go here, but this is not something we're changing, so we're going here, we're changing the value, we're indicating this number to push down, and then going back in the recursion, we're just collecting those two information. So we need to, again say that this then is the sum of 6 and 9, which is 15. And we can see that all the information, all this orange information that have ever been here in this vertex have already been pushed because we were going through this. So, this information is not longer something that we need to be concerned about. Then we'll go here to the right, the value will be changed for 16, and then we see that the recursion will go back to this knot, and again it needs to be changed so that it was the sum of 15 and 16, which is 31. And then let's say we have another query. Maybe let's go straight to the third one, it will be a bit more interesting. So 5 to 8, and we add 4. So, again, left child is not something that we're concerned about. And we know that the value here is 15. So it's the right value considering all the orange values in the subtree. So it's definitely right. And we're not changing anything. And then going to the right one, we see that we need to change 16 for 32. And we need to add to the children in the future 6. And then our recursion will go back to this node. So we again need to collect the information from the nodes, but from the new ones. So 15 plus 32 is 47. And then we can see that, going further down, every time going further down, when we go back in the recursion, we just need to actualize this value in the vertex. This is something that you can always do. I mean, sometimes it won't be necessary to do it if it was actualized beforehand, but you will, adding an additional if to check whether the information is new doesn't really make sense. We can just do it always. Okay, I think that's it about the range trees, sequence trees, segment trees, sorry. I will give you a task, and in the meantime, I will recover my code so that we can see how it looks like in the code, because that was a lot of information. So I think looking at the code would be something nice here. A task first. Okay, so let's say, just let me check which one was easier, because I have 2 tasks. Okay, I think it will be fine. So, okay, we have a task such that we have all zeros at first in a sequence. So we have 8 zeros. And then at each time, we can, choose the subsequence and change all the zeros for ones and ones for zeros. So basically make, I don't know if you've heard about XOR operation, but we can just do XOR 1 operation. But you can just, think about it, changing 0 for ones and ones to zeros. We can see that all of the values in a subsequence are zeros, so they all will be changed for ones. So we'll have 1, 1, 1, 1, and 1. I think that's it, yeah. And then maybe, we have a change like that. So that would mean that this 0 would become 1. And this one would become 0, and this one would become 0. And we have a lot of changes like that. And between any change we don't win, somebody can ask us, okay, how many ones are on a given sequence? So the input would look like this. We have a number n, and we have 2 operations. Either we are changing from A to B, all the values from 0 to 1, from 1 to 0. So we don't need to indicate any third value, because we already know that all the zeros will be changed for 1, all ones for 0. Or we're asked how many ones are on some subsequence A to B. Okay, I hope the task is clear. Again, if you know how to do it, you can indicate it by writing heart or plus or X or anything in this rectangle. And I will try to find my code. Try to, if you think you know how to do it, try to actually think about the implementation here, because it might be tricky. Okay, I will just look for a code and then I will share my screen again. If you know how to do it, try to implement it. And I can send you later a link to send the task, but the task is a bit more difficult because you may have might have really long sequence. So I think it was from 1 to 10 to the power of 18. The sequence is of this long length. So you need to do one trick to make it shorter. And then you can basically apply this knowledge. I can send you the link right now. Unfortunately, it's not translated. I've checked that. Oh no, just to 10 to the power of 9, but it doesn't really matter. Okay, so maybe let's quickly look at the code beforehand, and then we will talk about the task. So I hope you can see my screen. I think you should. Okay, this is the code for the buckets. So the task previously, well, with the buckets, and we needed this push operation there. I don't know if you still remember. If you don't, then I strongly recommend that after all the classes, you go again and look how it looked like. But basically, as you can see, the pushing down information, it's just, adding the changes. The changes table will be the one that is indicated the orange value. So whether we need to, push something down or not. And here we just, if we had to indicate to the children that they need to change, then their children also need to know they have to change. So the situation is, I will go here. I think it was here. Yeah. So, when we were crossing out this, it was blue value here. Then we also needed to indicate the blue value here for the child. So we are just adding to the child all the changes from the father to both of the childs. And this is this, and this. And then what we also need to do is actually change the child. So this will be this adding 2 plus 2, adding 2 times 2 to the 5, which was a bit different in the bucket task, because in bucket task we did have the minimus, not the sums. So the minimum only changes once for all of them, right? I mean, if we have the values 2, 3, 4, 5, then subtracting 2 will change minimum by 2 rather than by 2 times 4. It doesn't really matter how many numbers is this vertex in charge of. The minimum only changes once. So we were just, adding the change to the actual binary tree. So this orange value here. And then we need to clear up the changes. So as we were talking about before, we don't want this +2 to be to change the children twice, because it's just 1 + 2. We don't want the children to be +2 + 2. So we need to clear it. Okay, then this is the whole push operation, and then we have the add operation. As you can see, it looks pretty much the same as the normal segment tree. I hope you've wrote a segment tree at least once in your life. I will go quickly through the basics though. So we have a beginning and the end, which are the values that this node is in charge of. So, the 18 is in charge of all the nodes from 1 to 8. So the beginning would be 1, the end would be 8. The vertex is just the number of the vertex that we're in right now. So the 18 is the vertex number 1. So, it would be 1 here. AB is the actual query. So changing everything from 3 to 8, A would be 3, B would be 8. And then value is the value that needs to be added to everything. So if the node is, in charge of everything that is not is something that we are concerned about. So, for example, this 5 is in charge of everything between 3 and 4. Sorry. And we asked about everything between 3 and 8. That means that everything that is inside this vertex is something that we are concerned about. And in this case, this is, the basis vertex. So if this is the basic vertex, then we want first to indicate that the children will be changed. and also change the actual value of the knot. So it will be just, in this case, going to the 5, we would say, okay, we need to add +2 to all of the children. So that would be changes plus equals value. And then actualizing the binary tree. So adding 2 + 2. In our case, in the bucket case, it was just adding the value, not adding value times the number of knots. If we did have a task with the sum, we would add value times and minus beginning +1, because this is the actual size of what is inside this knot. Then, if we are not doing that, then that basically means that we are going to the children. And if we are going to the children, we need to push the value. So we're just, saying, okay, so we're going to the children, we need to push the value from the changes to my children. And we're just doing this operation that we talked about earlier. And everything else is basically the same as with the normal segment tree. So we're just finding the middle. And, if something from beginning up to the middle is something that concerns us, then we are visiting this child. And if everything between middle +1 and end is something that concerns us, then we're visiting the right child. And then after, after all the everything we've done in the left child and everything we can do in the right child, we need to collect all the information. So the thing that I forgot to mention about, when going up, we need to collect all the data. So here the value changed from 5 to 9. So going back, this won't be 11 anymore. This will be 15. So this is the line that does that. And then this is my code for taking out the bucket. So as you can see here, we're just taking all the data and adding it to the tree. And here there are actual queries. And we can see that we're adding the value of the rain to all of the buckets. And then while the root is, in my case, greater or equal than 0, because I did have at the beginning all the values with the minuses, and then I was adding the value of the rain. And if it was greater than 0, that meant that some bucket was filled up, but it doesn't matter. It's just that this was the case. I will go back to the task. Sorry, it was here. No, it was where it was. I've lost it. Yeah, here. Okay, so in case, where we did have non-positive value here, we're taking out the buckets. And while we have non-positive value here, because as you maybe remember, maybe not, we may have a situation where more than one bucket overfilled after one rain. So we need to take out all of them. And then, we're just putting on the output all of the values. But let's quickly look at the taking out the bucket. So what we are doing is we're just going from the first vertex and seeing which path. So, every time we're visiting some vertex, we are pushing out the values so that, we could actually visit the children. And then we're asking which, here, those two lines, is asking which of the two children is smaller. Because, if the first children is smaller, then the bucket is probably there. And then what we are doing is just we're taking out the bucket, so we're indicating the infinity value, and this is just the resolution table. So the result, indicating the result of the bucket, like this, like here. And then what we need to do is, actually in telling every knot above this bucket that we took out that the value may have changed, because if we have go like this and we take out this bucket and we have infinity here, then we can see that everything on our path previously was some -1, for example. And after changing this bucket for infinity, all of this knots will also have to be changed for some value. Depends what's on the path. So here it will be 3, here it will be 1, and here it will be 1. So this is what this while is doing. But the most important part is, those two operations. So the pushing, which is, as you see, not hard. We're just saying to the changes that the value here rose, to the changes in the right child that the value rose, and then actually changing the children. That's it. And then in the add, the only different thing that we're doing is the push. So we need to remember to push the values down. Everything else is the same. Depends on what we are doing on the binary tree, which is the name for the segment tree. We may also need this line. I mean, we may need it for the normal segment tree, and we always need it here for this magical segment tree that does have range queries and range changes. Okay, so that's it about the code. I can send it somewhere, I think, later. I will ask Luca. So that you could look at it at your own speed and see if you actually understand what's going on there. So let's go back to our task. You have all the resources to code it now. You should, at least. So try doing that. And if somebody doesn't yet know how to do it, I will explain it. Okay, wait. Okay, so what we know at first is that we don't have any ones, right? Any ones. So the whole segment tree will be just zeros. And now asking about any segment, we'll just have 0. That's fine. And then let's say that we have a change. For example, here. That means that all of the values here also need to be changed. But we don't want to do it all at once, because it would be the same as without pushing the values with the sum. We would need to actualize all of the nodes here, and we don't want to do it at once. So let's just find the basis vertices. So the basis vertices will be here and here and here, and let's see how they change now. So this vertex was previously 0, and there is just one vertex in this underneath, I'd say. So it means that all of the vertices that have been 0 here will be 1s. So, we overall have one vertex, and we know that we have one vertex of 0 and 0 vertices of 1s. Okay, that's a lot of 0 and 1s. I hope you got the point. So it means that from now on, we have 1 here. So we can just say, okay, from now on, this is 1. Here also, From now on, this is 1. And something more interesting is happening here, because we did have 2 zeros here, right? So number of 0 is 2, and number of 1s is 0. So all the zeros will become 1s, and all the 1s will become 0s. So we can just swap those two values. Now we'll have 2 1s, and we'll have 0 zeros. And remember, something that I forgot about with the sums, we also need to actualize all of their values above them. So this not, while going back, also needs to be actualized. This not need to be actualized, this not. But we are doing this in the meantime in a code like here. So here we'll just, collect the value from the left and from the right node. So we know that, we have 0 1s to here, 1 1 here. So we have 1 1 here. So the number of 1s will be 1, and the number of zeros will be, just everything else. So we know that overall we are in charge of 2 nodes, which is known because we can just take end minus beginning plus 1, as I told you before. And therefore we know that, everything we're in charge of minus the number of 1s is just the number of zeros. So we have 1 0, and then we can just add those values. So we have 1 0, and then 3 1s. And same here. So we know we have 1 1, 1 0, 1 0 here. And then we have 1 0. Sorry, I made a mistake here. 1 1 1 0. Okay. Because this is the 0, this is the 0, this is the 0. Perfect. And now so it means we have 3 zeros, because here we have 2 zeros and 0 1s. So we have overall 3 zeros and 1 1, which means that overall we have 4 zeros and 4 1s. Okay, perfect. Let's try then changing something else, right? So, oh, and I forgot about one thing. We need to also indicate that in the future, if we go to the children, they did go through 1 change. Because you see, those 2 vertices have not been visited yet. So we haven't yet figured out what value should be there. So we'll do that later. But we need to remember to do it. So we have 1 change, right? Okay, let's go further. Let's say we want to change everything, for example. We want to switch from the beginning to the end. All the 0s to 1s and all the 1s to 0s. So that would mean that the only thing we're visiting is the main root. So, oh, I made the mistake again. Here should be 4 1s. Sorry. So it would mean that the number of 0s and number of 1s would switch, right? I mean, for switching 4 and 4 doesn't really mean anything, but we're still switching them. This is how the algorithm will do it. And then we need to indicate that, hey, if we ever visit the children, they need to remember that they went through 1 change. And I should do it with orange color. Okay, let's go further. Maybe now we want to, go and change just the 4th one. So we'll do the change from 4th to 4th. So we see, first we visit the root, and we see that, well, that's not the vertex that is the basis, because it's too big. Sorry, I will just turn off the WhatsApp. Okay. So we're going to the children, and we need to push down this one. So we are doing the change on both of the children. So we are, doing this and doing this. So we are switching 3 and 1, which would be 3 and 1. We are switching 3 and 1 here, which would be 1 and 3. And we also need to indicate that in the future, our children also need to change. So we have one change, right? And then this change have already been done. So we don't want to do it again. And now going to the left child. We see that this is not the vertex that is in charge of everything we want. I mean, not everything that is in this vertex is something that we are concerned of. So we need to go further to the children. So we need to push the change. So we need to, because we didn't go into this if, so we need to do the push. So, we'll change 1 and 1, and then we'll change 0 and 2. So we have 2 and 0, right? And then we also need to indicate for the future that, it was 0 and 2, so it needs to be, yeah, it needs to be 2 and 0. And this change was done. And we need to indicate for the future that their children will also need to be changed. And this was already done, so we don't have any changes. And then left son doesn't really concern us because we are not going any further, so we're not pushing down the change. The change is still there. Maybe we'll do it later, maybe we don't want. We're going to the right child. This is something that is of our concern. And we're going further down, so we need to push the change. But hey, we already did have a change here, and we have another change. So, we can either stack them up and say there were 2 changes, or we can also see that 2 changes mean no change, right? Because changing from 0 to 1 and from 1 to 0 is going back again to 0, and we can just, store this value modulo 2. So this was changed 2 times, so it's not changed at all. So we can push 0 down. And then going to this vertex, it has not been changed because we pushed 0. We pushed 0, so we can erase it. And this value has not been changed, because we did have 0 here. So we are saying, yes, we don't have any ones at the range of 4 to 4. So we're basically doing everything we did before. But the value that we want to push down is the number of changes, modulo 2. So it was easier. And then the thing that we want to store in the vertexes is not the sum, rather the number of zeros and number of ones, and then we can change them. We can also just store the number of 0 and then, calculate the number of ones. What's easier for you? I think changing is a bit easier to code, but I mean, it doesn't really matter, right? Okay, that's it for the task. Who understood it? Can you please thumbs up? Okay, perfect. Okay, so we have a bit of time for another task. Unfortunately for this task, I don't think I have a place to send it. I think it was originally from some code forces. I'm not sure. I will try to find it later. And also afterwards, I will give you a few tasks from the Polish Olympiad that are also for the tricks on range race. I tried to give you more interesting ones during this lesson, but there are so much more. Okay, so we have a bakery now. We are bakers, and we have, some bowls for the cakes. And let's say that we are using a machine, because, it's easier to use a machine, right? So what the machine can do is put some layer on some subsequence of the balls. So let's say that we would put a layer of number 2 to all of the cakes here. So, it would be a layer 2 here. And then maybe, we can we will do a query where we are adding a layer number 1 to all of those cakes. So it would be, those would be just 1, but here we would stack up the layers. So it would be 2, and over it would be a layer 1. And then maybe over all of the layers we want to put, I don't know, over all of the balls we want to put the layer of number 5. And that would mean that here is just 5, here is 2 and over it 5, here is 2 and over it 5, and here is 2, 1, 5, 2, 1, 5, 1, 5, 1, 5, and just 5. And the first question, the first task is, okay, we have a query such that we're adding the layers, and in between we have a question about some particular cake. So we're asking whether, for example, the cake number 3 is pretty. And a cake is pretty if the layers are stacked up in an increasing order. So, the 1, 5 is pretty because 1 is smaller than 5. So we have an increasing sequence. But then the cake here is not nice, is not pretty, because we have layers 2, 1, 5. So 2, 1, 5 is not a strictly increasing sequence. So for 3, we would say no, it's not pretty. But for example, 7th, we would say yes, it is. And the limits are standard. So like we have 10 to the power of 5, 6 queries, and then the number of balls is also in range of from 1 to 10 to the power of 6.
There is no way to erase a level.
No, there is no way to erase a level.
So a bad cake is forever a bad cake.
Yep.
Okay.
That's quite crucial information. It's really nice you've seen that. Okay, and here it will be, again, a rectangle of flexing. If you know how to do it, you can indicate it. Again, be careful because it may have some traps. So if you see it right away, that's good. But just think for a moment if you thought about, all of the pushing, all of the stacking. Remember all the things you need to know in order to be able to do the tree. And if you know how to do it, then you can now think about how to answer a question. How many pretty cakes are on some range? A to B. Again, this one even have more traps, I'd say. When I was thinking about this task before I got into one, okay. Okay, I will give you some clue. Yes, we have 20 minutes, I think. So it would be nice to, finish the task. So first thing is that first what you should do with those kind of tasks is remind all of the steps that we need to do for the range tree. So first thing we need to be able to do is, for example, stack up the information. I mean, the information will be pushing down to the children, right? So, if we have layers 2, 4, 6, then maybe there is a nice way to compress this data in order to be able to push it down to the children, right? So the pushing. And then also storing information about the layers. So an easy way that I think most of you should be able to come up with is that we could just, remember all the layers that have been put. It will be long. We need to make it faster, but this is a valid reasoning that would take the complexity O of n squared. And maybe, maybe we can somehow compress the data to make it faster. So what I mean by this is, if we are adding here, if we're, adding to all of those knots, the layer 2, then in our tree, we would just remember that I will maybe, I will draw a tree. Okay, so we are adding from here to here the layers. So we could just, remember this information. So we are having layer 2 here. And also we need to remember to add layer 2 to the children. Okay, then we're adding the layer of 3. So what we could do is we're doing this on range here, right? So we're, going down, we see that we need to push this information down. So we'll, just push it and tell the children, okay, you have a layer of 2. And then we don't have any information to push further. So we can just forget it. And we're going down, this child is not of our interest. We're going to the right one, and we can see that there is value 2. Nothing to push down. I mean, okay, we can push the 2 down, but it doesn't really matter. So what we would do is say here we added the layer 3, and we also need to add layer 3 for the pushing down. And an additional, and maybe let's just finish it up. So then we're going back, and then we'll see that, here we don't have really anything to push, and we don't really have to remember that the information about any of the children, because we can just collect the information later. I will show you in a moment what I mean. Let's just finish it up. So it will be 2 and then 3 here, and then we could, just trying to answer whether a cake is nice or not. We will just start in a knot and then go up and go up and go up and see what layers were added. So basically, I would even say that for this variance, for the first variance, we don't even need pushing. We just need to remember the layers that were added. So maybe we'll do it like this. So, you know what, I will just do a nicer tree, nicer, bigger one. Yes, I don't think that's clear. For the first variance, actually, we just have to remember what layers were added. And we can stack it up, but we can also, you know, just we don't need to store the second value. This is what I mean. Sorry if I made you confused. I will try to explain it again. So adding a layer to here, it will mean that, you know, the layer 2 was added here, the layer 2 was added here, the layer 2 was added here. And then adding layer 3 here, the important thing is that the order unfortunately matters, right? So we can't just, you know, take those vertices and call it a day and say, okay, this is 3, this is 3, because then looking at the layers, this here, and looking at the layers here, we would say the layers are 3, 2 in the first vertex, and the layers are 2, 3 in this vertex, which is not right, because exactly the same operations were done on the fourth vertex, and exactly the same operation was done on the fifth vertex, right? So while going down here, we will just push down this information. So we are pushing, but we are just storing one information about the layers. We don't need to store the information separately for the pushing and the information in the knot. This is what I meant. Sorry for any confusion. Okay, so let's push down this information and say, okay, this does have layer 2. And what we can do is that we can just add layer 3 now, right? So, you know, this to the layer of 2, there will be added a layer of 3. And here will go up. Sorry, this 3 is still the information in this vertex. So this vertex just have, you know, both of the values, maybe a vectors, you know, maybe the each knot will have a vector, and then we'll just storing all of the information. So going back, we don't need to actualize anything because we're just pushing down the values. And yes, this is not something we need to take into account. Nothing to push, also nothing to push, but we need to add a layer of 3 here. So we're just, you know, adding to a vector 3. And then let's say that we are maybe adding 4 to all of the vertices. So a layer of 4. And what we will do is just ask this vertex and say, okay, we're adding a layer of 4. And then what we can see, for example, adding a layer of 5 to the vertex 5th, what we would do is we go to the root, we see that there is a 4 to push, so we're pushing it. Okay, and then, you know, it's already pushed. We don't need to go to the left one because it doesn't concern us. We just go to the right one, and we see that we have a 4 to push, so we are pushing this 4. Stacking up the information here in some vector. Later we'll tell how to make it faster, but for now we'll just remember everything. And now we can see that right is not of our concern, we go further here. And we can see that 3 and 4 is an information that we need to push down. So we'll just, stack up the information, 3, 4 here, 3, 4 here, and we'll forget about this information. Okay, so we've pushed the information down, and then we go to the left zone, which is something that, a vertex that is over the 5th vertex. So it's something that concerns us, and we just add this information to the stack. So in this vertex, we have a stack of 2, 3, 4, 5. And you see that, pushing this vector on the top of the vector that is in our children will kind of not only store all the information, but in the proper order. Because if we're going through any vertex, we're pushing down the information so that the value that was previously here would be first, and we would actually add this 5 over the top of 4, not underneath it. So here, the thing is that order is really important, and we can't just, abandon it. Okay, so we are storing all of the information about the layers, and now asking about some knot, about some cake, what we need to do is actually go, all the way up and see what are the layers on our way. So for example, going up, we would see that all of the layers here is just 4. Go up from this, you would see that it's 2, then nothing, and then 4, and then nothing. So it would be 2 and 4. So we not only are reading from the knot, but also we need to add all the vectors above, because, if we did it properly, they would be just pushed to this knot. And this is something that may work in the complexity of n squared, because we need to push all the information. So, the worst case scenario will be pushing it each time, each query, everything. So maybe we had it here, we'll push it down. Maybe we'll go here, push it down. So, we'll go through the whole process a lot of times. So what we can see is actually that a valid information is that some cake was already ruined, right? Because if it has already been ruined, then it's not something that we can fix, as somebody previously mentioned. So the first information that we can store somewhere is that, the cake has been already been ruined. And you can see that it would be valid for all the cakes below. So like if we have 4 here, and then let's say we try adding to such subsequence 1, and we would go here, see, okay, we're stacking 1 over 4. So that's not something that is valid. So this is already ruined. We can, let's say that it's black from now on. And everything below it is also ruined because of those stacking 4 and 1. So, this will make our life a bit easier, because that means that if we ever go through that point, that means that a cake is ruined and we don't need to do anything further. If it's already ruined, it's not something that concerns us, right? So that's already a bit faster. Okay, what else can we do? We can see that, if we have layers 1, 2, 3, 4, and then we're trying to add something here, then it's ruined if and only if it's smaller or equal than 4. So anything below 4 doesn't really concern us, because it could be, I don't know, 2, just 2. It could be 2 and 1. It can be just 3. Doesn't matter. It matters that it's in a particular okay order. It's not yet ruined. And the question is what we are adding on the top. If we are adding something greater than 4, then it's okay. And if not, then it's not okay. So maybe that's, we don't need to store all the information and we can somehow compress the data. But be careful, because it's really easy to get into the trap here and just store, the highest layer. And unfortunately, that's not something that is correct, because we need to store both the highest and the lowest layer. I will show you in a moment why on some example. But yeah, just storing those two values, we can quickly check if stacking up those two over some other two will give us a cake that is ruined or will give us a cake that is pretty. So let's say we have a situation where, we have a range tree and all of the information that we're doing is firstly we're adding here +4, let's say. So, and let's say that we're just remembering the highest layer now. So, sorry, not +4, just the layer 4. So we would remember here the highest layer is 4, right? And then let's say that we're adding a layer of 1 over the top of everything. So we would remember here, okay, we're adding the layer 1. And then let's say that we're adding over everything a layer of value 5. And remembering only the highest value, we would just, erase this one and say, okay, it's 5. And then maybe we're adding a value of 6 over just this one cake. Then what we are doing is, going from the roots, pushing this value 5 over this value 4. That's okay. We can put 5 over the 4, right? So we are saying, okay, the highest value now is 5. And highest value here is 5. And, we don't need to push anything further. Okay, we still need to add the 6, and hence we are pushing down 5. Left doesn't concern us, we go to the right, we are erasing the value 5, pushing it down, and then stacking 6 over the 5, which means that everything is fine. Here it's 6, here's 5, 5, 5. But hey, we forgot about the 1. Where did we make a mistake? Well, we can't, we did have 1 and 6 here, we did have 5 here, and what we did is we just remembered the highest value and we said, it's fine, I can stack 5 over 5, 6, right? But there was also a value here. So we need to remember the smallest and the highest one. Look that anything in between those wouldn't really matter, because we know that it's correct or not. It doesn't matter. We need to know if we can stack up 1, 6, and anything in between over 5. So that's the trap. Here with the second one, I think there are even more traps. So be careful. Be careful. And I hope you didn't get into that one about remembering only the highest layer. So yes, and then every operation of combining would be just a case of looking whether, the smallest layer is still greater than the largest layer here. And if it's okay, then we can just combine it, right? And remember the smallest from the child and the highest from the father. And then pushing those two values, which means that every pushing is just, checking for values, which is still a valid complexity, because that would now mean that each query is just done in log of n time, times obviously the number of queries. And we don't need to go through the whole stack each time. I mean log n times 4, because we are checking all the foreign information, but that it doesn't really matter. Okay, I think I still have a lot of the tasks, but I mean, it's 7 and you're probably a bit tired. So I will, just give you them. If you need any translations, I've checked and ChatGPT should give them the translations just fine. But if you have any questions, I will tell Luca to somehow give you my contact, or you can ask Polish people here, just any Polish people to translate you. But yeah, Polish tasks for the Olympiads are really nice. So if you want to practice, then I strongly recommend taking a look at them and try to think what would happen if we have many queries about many pretty cakes. So we're not asking about that particular one, whether it's nice or not, but we're actually asking on some range how many nice cakes are. I will give you a clue that it's kind of similar to the bucket one, to the bucket task, but I would say there are more traps, like like these layers that you can get into, and in bucket there weren't really many. Okay, I have 3 more tasks from the Polish Olympiads. I will send you the links. I think Luca is posting them on the Olympiad site or workshop site. So I will give him the links. He will post them, and 2 of them, as you can see, are translated to English. So you should be fine. One is unfortunately not, but it's a really nice task. So just ChatGPT, I guess, and you can submit it here. So it's really nice. I can quickly show you. You can obviously choose file or just paste the code. Then you choose the programming language, and then you can just submit. In the submissions, you will have your score. That's it. You need to set up the account though, unfortunately, but it doesn't take long. And you don't need to be a high school student or anything to do that. So you should be fine. Okay, thank you really much for the lesson. I hope you understood everything. If not, you can always just stay afterwards also, and I can try to explain it to you further. Thank you for the classes, and I hope to see you again sometime. Have a nice evening, guys.